Good morning. Good morning, Jocelyn. Good morning, Gabriella. Awesome,
Good
awesome.
morning.
Good morning. The double, the triple actually are awesome. Good morning, Sydney. Good morning, Effie. Good morning, Cartman. Good morning, Melanie. Good morning, Nadine. Good morning, Mohammed. Good morning, Yaverbaum. Good morning, Norma. Awesome. Okay, let's do this. Let's do this. Good morning, Angelina. Good morning, Effie. Good morning, Nadine. Good morning, Melanie. Good morning, Sinead. Good morning, Jibo. Good morning, Chanel. Good morning, Jocelyn with the double. Norma with the double. Teresa, good morning. Sydney with the double. Mohammed with the double. With the triple if you count me in there. Okay. Is that everybody? Okay. Awesome, awesome. All right, I want to get straight back to, and again, exams in progress. I'll just say that, not forgotten. Just saying that. Um, um, yeah. So I want to get back. I know what I was doing. I want to get back to Newton's laws, specifically to Newton's second law, to specifically to how to draw diagrams to set up and expand the left side of Newton's second law, like as it says here on the top of the board. Like it's all about, as I said yesterday, it is all ultimately most Newton's law problems, most force problems, um, are about using our understanding of forces to predict and compute acceleration. And then once you have acceleration, going back to all the material we've been studying for the last 2 months to infer from an acceleration a velocity and therefore a position and a time. Like, just to remind you again, all of physics for the rest of our lives, all of physics. Sorry, I know someone's here. Sorry. Okay. All of physics is about where is something going to be when. That's it. That's all of physics. What are the space-time coordinates of this particle? That is physics. So for a while, what we've been saying in the class is, oh, the way to know where something is going to be when is to know its acceleration right now. Like that's really the premise of everything we've been doing to this point is if you know the acceleration right now, you'll know where it will be later. Or, by the way, I should really make a big point of saying, or if you are solving a crime, if you are a forensic science student, then you're not trying to predict where something will be when, so much as you're trying to retrodict where something was when, right? Like if the bullet is here now, where did the bullet come from? Yeah, or if the blood is spattered here now, where was the blood 5 minutes ago, or et cetera, car collisions, et cetera, right? But either way, we are trying the whole underlying meaning of physics for forensics is you're trying to compute the space and time coordinates for particles. The, Up until now, the concept is the way to do that is know a particle's acceleration at any given point in space and time. Now, what we're saying is the way to know something's acceleration at any given point in space and time is to know all of the forces acting on the particle at that space and time point. Right? Right. So now it's all about F net equals ma, the sum of the forces acting on a point of mass gives us the acceleration of that point mass at a point in space at a point in time. Okay, so it's all about F net equals ma now, right? And then what I'm saying, and it's all about the sheet of homework that you all just turned in. Thank you very much. Totally know it. Well, as you see, you all just you really on top of things. You class, you like. Anyway, so the homework that you just turned in, and again, it might not be perfect, it might be done, and of course you haven't gotten any feedback because you just turned it in, but if you did a thorough responsible, self-sufficient document first draft, then you got a ton of points already, and then we're going to go back and we're going to start going over it now or continue going over it now, and then you'll be able to do revisions for the rest of the points, blah, blah, blah. So that sheet, Newton's laws, all these problems, it's all about F net equals MA. But really, what I'm trying to drive home right now, before I flip screens and start doing diagrams and computations again, what I'm trying to emphasize right now is the F net equals MA, Newton's second law. It's really simple, but it's not easy. But it's really simple. And actually, it's much more procedural than like anything we've done to this point. There's like a whole procedure for unpacking and applying this Newton's second law, F net equals ma. And the key, the essence of that procedure is knowing what to plug into the left side of F net equals ma. That's where all the action and thought and analysis and step three and everything sort of happens from here on in physics, is what is going to go into the left side. What are the forces, magnitudes, and directions that I'm going to plug into the left side of F net equals ma? And the way to answer that question, the way to resolve those thoughts unambiguously is by drawing diagrams. So what we're going to get into now, that means diagrams. I don't even mean rough sketches that give you kind of a sense. I mean strict diagrams that follow rules that will do the thinking for you if you trust the diagrams. So, good morning. Sorry. Good morning, Alexis and Mohammed. If I didn't, no, I said Mohammed. Good morning, Alexis. Sorry. A quick screen share so you know what I'm talking about, or in the recording you do. And then we'll go back. So what I'm doing is this. Right, we're on this sheet here, which again, thank you. The huge, overwhelming majority of you, like almost all of you, just totally turned this in. So thank you so much. And where we were yesterday is right here in multi-force warm-ups, an apple on the table. Am I right? Yeah. Okay, the apple on the table. So now it's asking you for these. So we got an apple on the table, and first it asks you for a picture of the situation. So yeah, like we're still physicists. We're still doing five-step method for solving things. So you first draw step one, DFP, like yeah, just the sketch of what's going on, and you label the facts and that it's 3 kilograms or 0.5 kilograms, et cetera, right? And then step two, you say what the question is. Step three, I can tell you right now for any one of these problems, step three at the very least is Newton's second law, probably also Newton's third law. That's step three. Then step four, when you start to analyze, that's when I'm telling you right now, you can start subdividing in your mind step 4A, step 4B. These will be diagrams. Step 4A will always be a system schema. It's not just a picture, it's a specific type of diagram that actually starts to analyze things for you. And then step 4B will always be a free body diagram. Okay, so it's telling you to do that right here. That's what I want to explain in detail right now. Is this system schema, and FBD, free body diagram. That's what I'm going to talk about right now. So, with your forgiveness or indulgence, I'm going to switch the screen back. So that's what we're doing now. Okay, so I'm switching the screen back. Give me a second. Hold on. Um, and remind me, I think this is homework 8, right? Please tell me in the chat if I'm wrong. I think I think it's homework 8, but please tell me in the chat if I'm wrong.
It's homework 7.
Oh, thank you so much. Oh, and that was voice. That was like, and respectfully corrected. Literally, I think that's like 3 portals you just got points for. Thank you. Homework 7. Thank you. And by the way, who? Was that, I don't even, was that not that it mattered. Was that Gabriella? No, it wasn't. Okay.
That was me, Norma.
Norma, thank you. Okay, sorry, not to. Okay, great, because I wasn't looking at the great. Oh, and there's others of you. Okay, not to get that. And thank you, Mohammed, and thank you, Sydney, and thank you, direct chat person who shall remain nameless. Please, all of you. I know this is ridiculous, but please, all of you, submit for points for that. Like, really, you deserve them. Thank you. Okay, I'm going on. Apple on table. Okay, okay. I'm going to. So first, we're supposed to draw a system schema of the apple. One second. Sorry. Okay. I'm going to, okay, so system schema. I'm going to say the rules and I'm just going to draw it. Like, okay, so here's how you do a system schema. First, you draw a solid circle representing the object of interest, the object that we're talking about. Specifically, what do I mean by the object of interest? What I specifically mean is the M, the mass in whose acceleration we're ultimately trying to compute. So the m in F net equals ma, you draw a solid circle to represent that. So here we go. Oh, Jesus. Okay, so that's in this case, it's the apple. So I'm just drawing a solid circle representing the mass of the apple. That's the first step I always do in a system schema. Okay. And I do recommend writing these rules down as rules because they are literally rules. And some of you are going to be relieved to find out that if you just used to and practice these rules, then you just do that. Like you don't have, they do the thinking for you. So you first draw a solid circle representing the M that we're dealing with. Then every single time, rule number two, okay, every single time you draw a dotted circle representing planet Earth, more specifically, you might argue representing the entire Earth, like all of the mass of the Earth, or if in your head you're drawing a dotted circle representing the center of the planet Earth, like you're picturing that all of the mass of planet Earth is like concentrated really intensely at a point in the center of that sphere. I mean, maybe I'm being a little technical now, but what I'm saying, and you're going to draw this dotted circle anywhere on the page that you want. So I'm going to do that right now. Like, here's a dotted circle anywhere I want. Um, dotted circle, and I'm going to label it. Like, you could label it EE for entire Earth or CE for center of Earth. Okay. Um, or PE for planet Earth. It's going to be in the diagram every single time. Hard and fast rule. We're doing classical mechanics. For the rest of the semester, any problem we do in the context of Newton's laws is being done on the surface of the Earth. So the Earth is like always involved. It's always there. So we draw it first with a dotted circle. Okay, anywhere we want on the page. That's rule number two. Then rule number three, we're going to draw a dotted circle for each and every piece of mass, every piece of material, physical object in the world that we think is somehow um exerting a force on the apple, which really means in English 100% rule, we're going to draw a dotted circle for every single object in the world that is in any way touching the mass, like is in physical contact with it. Okay. So in this case, that would be the table. Like, and there could be a million, or there could be only one, or there could be none in some cases. In this case, there is one. It is the table. The table is touching the apple, the mass. Therefore, I draw a solid, I mean, excuse me, a dotted circle for it, and I label it like table. Now there's no, and I check, are there any other objects that in any way, like in any relevant way, in any way that's been mentioned by the problem or seem to be figure or have any numbers associated with them? In other words, I'll even admit, because someone brought this up like in direct chat like a week ago, like is there air in the room that's probably touching the apple? Yeah, there probably realistically is air in the room that's touching the apple. First of all, though, I would caution you that we're in classical mechanics here. Like we're doing. Oh, sorry, someone's here. I'm sorry. I'm sorry. Sorry. We're doing classical mechanics, Newton's laws. So 99% of the time, anything that's like a gas or even probably a liquid, anything that's a fluid, probably we're not really recognizing as relevant in the problem. That's number one. But number two, the problem didn't say anything about air. Like I'm not saying don't get me wrong. Do not think for a minute that physicists can't deal with like air as a concept or as a, but the problem didn't say anything about the air. It didn't give any numbers associated with the air, right? So the air is not playing a role. So in other words, the only thing that's been mentioned that we have any information about that is in any way touching, literally touching the apple, is the table. So I drew the table. I mean, I drew a circle representing the table. So that's it. This is now all of the circles I'm drawing in the diagram. I'm going to go back and explain the reasons for all this in a minute. But right now, what I'm saying, and I really do encourage, and again, remember, this is a portal too. I don't remember if it's called like well noted or something, but if you're writing down, I would encourage you to write down these rules that I am not crowding the page with. Um, they'll serve you really well. And then, take a screenshot of it and submit them for points. So rule number one was solid circle representing the mass in question. Rule number two is dotted circle representing the entire Earth. Rule number three is dotted circle. Sorry, I'm actually doing it backwards. That's weird. Sorry. You know what? I usually do it the other way around. Usually, sorry, it doesn't really matter. It's just weird that I actually mean it the other way. I usually do that the mass is the dotted one and the other two are solids. I don't know why I'm sorry. It's too early in the I mean, that's a style thing. You could just be whatever you do, just be consistent with it. But okay, so circle one, dotted circle for the mass. Thing two, rule two, solid circle for entire Earth. Rule three, solid circle for each and every object that is touching, literally touching the mass. Okay, now that we've done that, now we're gonna start drawing lines. So rule number four, draw a line connecting entire Earth to the object. So I do like this. Okay, there's a line there. That's it. That was rule number four. Rule number five. Now, this is a little bit complicated. Rule number five is now one touch, one line rule, but it has two exceptions. Okay, so rule five, I'm going to say it again, is the one touch, one line rule, but it has two exceptions. Hold on, I'm just switching the screen. Okay, one touch, one line rule. The one touch, one line rule means that for every touch that you see in your diagram, you're going to draw a line. So it is that simple. So for example, the table is touching the apple. So I'm going to draw a line connecting the table to the apple. That's what I mean by the one touch, one line rule. But it has to be noted that there's always exactly two exceptions to this rule. One exception is what is the line we already drew, that there's a line between, always a line between Earth and your object, even though there's no touching going on there at all, right? Like, and this is why we always sort of draw the Earth first, and we sort of draw a line from the Earth first, because it's always, because the Earth is always pulling on everything through this phenomenon, this force that we call gravity. We're all so used to it. It's always there. It's super important. But it is a little bit, just because we're used to it and it's always there, doesn't mean we fully understand it. It's a little mysterious. It's a little weird. It's the one force that's in every single situation without any touching at all. So it's one exception to this rule. This rule, like, see where I'm going with this is that the lines represent forces. So it is a rule that wherever there's a touch, there's a force, and conversely, wherever you think there's a force, there must be a touch, except that gravity is an exception to that. Okay, so we have a one touch, one line rule. Exception number one is gravity, so we always just get the gravity out of the way for the Earth. We draw a line for that first. But now, here's the other exception, much more subtle, a little more tricky. The other exception to the rule, to the one touch, one line rule, is that when, and you may want to write this down. This is the other, and it's a hard and fast exception. Like this rule, it's an exact rule with exactly two exceptions, and then it's universal from there as long as you understand the rule and the two exceptions. The rule is for every one touch, there is one line. Exception number one is Earth is a line without a touch. And exception number two is whenever there are two rough surfaces pushing against each other. Whenever we have two rough surfaces pushing against each other, then we're going to have two lines. Now, let me expand on that for a second. When I say two rough surfaces pushing against each other, first of all, I mean surfaces, like two-dimensional, like planes, like not a rope pulling on something, like a sandpaper pressing on another piece of sandpaper or something is what I mean. That's number one. Number two, when I say that the surfaces have to be rough, I specifically mean they have to be rough in a way that the problem or the scenario or the experiment actually explicates. Like it has to be mentioned that they're rough. And a lot of times, as we get more used to this, you'll see you might even probably have been given numerical information about their roughness, like a number that we call a coefficient. So the surfaces have to be like explicitly rough. They have to be surfaces and they have to be pushing on each other as opposed to pulling. Like I don't mean magnets. I mean like sandpaper or like a table pushing on a hockey puck or something. If you have two surfaces that are rough and that are pushing on each other, then that situation gets two lines. Okay? And I'll explain why in a moment. But that's the other exception to the one touch, one line rule. Everything that is a touch gets a line. Everything that's a line is a touch, except Earth is a line without a touch, and rough surfaces pressing on each other are are touches, but they get two lines. Okay, now I will explain why that is, but before I do, in this situation here, we have a table, we have an apple on the table. I would argue that those are two surfaces. I mean, the bottom of the apple is pushing on the top of the table, or the top of the table is pushing on the bottom of the apple. That is two surfaces pushing on each other. But in this particular scenario, the problem never said anything about roughness or friction or anything like that. So I'm not worried about it in this situation. So in this situation, it's just a touch. So I'm just going to put, sorry, so I'm just going to put a line. Okay. Now, first of all, I am now done with my system schema. That's it. Like I've now followed all the rules. The rules were, circle for the mass, circle for the earth, circle for every and any other object touching the mass, then lines connecting all the objects, one touch, one line with the two exceptions. I've done the diagram. First of all, what is the point of this? Like, I mean, it may seem kind of stupid or like a lot of time to spend on something this simple. The point of this is now, if I've done this correctly, I can now look at the. Hold on, I'll write this down. Ay, God. The purpose of this, and I really want, please indulge me and hear me on this. The purpose of this is that now literally every single one of these, the purpose of drawing the circles was to get the lines. The purpose of the lines is that each and every line is a force that is going to get inserted into the left side of F net equals ma. And not every single line will be recognized and numerically expressed in the left side of F net equals ma, and nothing that isn't a line will go into F net equals ma. So in other words, what this really, now we still have more to do, but it may seem kind of like, it might seem like I'm like over talking something right now. But the thing is that, again, going back to the something that I think people are noticing more and more as the homework gets thicker or the exams get thicker or whatever, like the thing about physics is setting up the math is the hard part for a lot of people, for most people. Knowing how to begin a problem, setting up the math is the hard part for most people. The math computations, especially if you've learned the math skills or you've taken the math class, often is not actually the part, it's the part that scares people at first, but it's often really not the part that people struggle with. What we all tend to struggle with is how do I set up the math? Now, and especially with F net equals MA, there is the math is just like divide F net by M and you'll get A. Like really, the math is not the issue. The issue is what do you put in for all the F's, i.e., what is a force and what is not? What counts and what are the numbers? What are the directions? So, what I'm saying is this is a procedure, it's sort of step 4A of the procedure of knowing exactly what is a force and what is not. Everything that's a line is going to be a force that's going to go into the law. And really what we're really saying in the background is if you want to know if you want to know what forces are acting on an object, what you really got to do is think about all the other objects in the world that are interacting with it. Like that, right? That's the lesson of Newton's first law and Newton's third law, is that a force on you is an interaction on you from something else. And when I say something else, I truly mean like a thingy thing, like a identifiable, material, tangible, or object, like another table or a baseball bat or a car, something that is actually going to touch you plus Earth, right? I'm trying to make something as abstract as forces get really concrete with this diagramming technique. It's basically forcing you to find out what the forces are by first asking you to draw all the objects in the world that might possibly be exerting forces. So the system schema gets you to know what the forces are by giving you lines that represent forces. And it gives you those lines by first asking you to identify the objects that are interacting through those lines. Okay, that's all it did. I'm going to move on now. That's all it does. But I mean, if you can really, whatever, if you can take this seriously, it'll help save you a lot of headaches. And especially those of you, if any of you had that experience, like in the earlier units of like, I kind of get what's going on in this class, but I like kind of never know how to start or like what he wants me to do. Like, this is actually going to be more straightforward for some of you if you just keep paying it. Like, it's a more clear algorithmic like procedure. So you do this. Um, so I now know, looking at the situation, that when I eventually go to do F net equals MA, I'm going to have two things that are going to get it plugged into the left side. Like, because there's two lines, there's going to be two forces. However, what I don't know is like directions they're pointing in or what their magnitudes are. Like very deliberately, this thing, I just drew Earth wherever I wanted. I drew the table wherever I wanted because I'm just trying to get, I, I'm just trying to identify forces. So now, sorry. Okay. So now, sorry. And there's things in the chat. Hold on. Oh, wait. Oh, okay. There's good things in the chat, and I could tell from the chat, which we're going to read out in a minute. I could tell that some of you have done like some good internet research to give you. Well, obviously you must. I mean, but yes, good questions. Hold on. All right, so I'm going to read the chat. Although let me just read out what I'm saying here on the board is we're next going to draw what's called a pure free body diagram. Because then even from there, we're going to draw yet another diagram called the component free body diagram. So we're going to draw a pure free body diagram. And the thing I'm saying here is, and we use the system schema to do that, every single line in the system schema will become an arrow of a vector arrow in the free body diagram. In other words, to get the whole purpose of this was to basically to get a count of how many forces are there. If there's two lines in the system schema, there's going to be two arrows, two vectors in the free body diagram. So that's where this ship is headed. And the purpose of those arrows will be to get us magnitudes and directions. Now, good questions in the chat. The first in the private chat, and please give yourself points for all these questions. The first, and all these, by the, also, I want to say, all these questions that are in the private chat, I totally get that you, any one of you should have been, every one of you should have been proud to ask this question, just so you know, like, it, you should not, I'm perfectly happy for them to be in the private chat, but that's for your sake to like there's nothing embarrassing about these questions at all from my point of view. Like I would be proud to share your name with every just so anyway. But the first one is the first question in the chat is, did I say that the solid circle was for the earth and the table? I sort of I bumped what I generally do is I do a dotted circle generally for the actual mass in question, which would be the apple in this case. And then I draw solid circles for everything else. In this case, for some reason, when I started, I did the reverse of that. And it's okay to do either as long as you're consistent, like distinguish the actual mass in question from all the other objects. That's what we're trying to do. So I generally do a dotted circle for the mass, and then I do solid circles for the earth and the table. The earth and the table would get the same kind of, I mean, so this is what I did. So the earth and the table would get the same kind of circles because they are both objects that are separately interacting with the mass in question. I don't know if that answers it, but I mean, that's my answer. But then there's a question that says, why? Now, this is a very good question. And this is coming from someone who has either seen this before or like looked on the web, like in a responsible way. Because someone's asking now, why didn't I put a line connecting the table to the earth? Yeah, which I did not. I did not put a line connecting the table to the earth. Now, here's the thing. I'm even aware that on the web, sometimes they do that. Like some websites will do that. I, I don't think you made a mistake by going on the web or looking at those sites. I think that is a big mistake on their part, honestly. Like, I mean, I get why they're doing it. I get why they're doing it. But I think that leads to huge misunderstandings and defeats the purpose. So I'm not criticizing you, but I am criticizing them. I am saying the reason that I would never do that, I never put a line connecting. I mean, let me back up. It is true. It is true that planet Earth is pulling down on the table. I'm not denying that. Like, that is true. Like, the table does have its own weight. It is subject to the gravity of the Earth, but that does not play in any way into the calculations of this problem. Like, I mean, not only does it not play into, like, we're not going to plug that into the left side of F equals ma. And not only are we not going to, but in fact, that's exactly the kind of confusion that is common and that we're trying to avoid by this type of diagram. What this, like, really, like, we're trying to figure out exactly what to plug in to the left side of F equals ma. And when I'm here to argue to everybody, and it is a subtle point, like, again, I'm not criticizing any, like, I can see why they do that. I don't think they're stupid for doing that, but I think they're missing the point when they do that. Because the common confusion that we're trying to get around here is that the thing that we're trying to get to is that F net equals ma means all the forces acting on you produce the acceleration of you. Like, if you, or put another way, if you, like, you are some object, you are an apple in this case. If you want to know the rate at which you are going to accelerate, what you need to know is how hard you are being pushed and pulled by every force that's coming into you from the world. And that's it. What other objects in the world are doing to each other does not affect your acceleration. Or let me go a step further. What you're doing to other objects does not affect your acceleration. F net equals ma means all the forces happening to an m produce the acceleration of that m. So but what people are always confused about, like, what are those forces? So all we're trying to do in this diagram, but it is we're trying to break through the confusion and say, we only want to be focused on what is happening to the apple. So the table is touching the apple and planet Earth is pulling on the apple. That's what's happening to the app. And if I sound like I'm yelling, I'm sorry. I'm yelling because I'm excited because, like, this is like the point. This is the thing that's hard about the issue that we're trying to like unpack with this picture. So I am aware that on the web, like in this picture, sometimes they'll draw a line connecting the Earth to the table. But to me, that is so confusing and defeating because I don't ever in my calculation of this want to put in that force. Like, that would be relevant if and only if someone asks me what's the acceleration of the table. Do you see what I'm saying? Okay, so please don't. So um I don't know if that so you oh, great. Thank you for responding. Okay, that is points to the closing conversation. Okay, thank you. But I think that, and that was a perfect example. I'm going to go on. That is a perfect example of whether it's in the direct chat or not. That is, I know that question is relevant to everybody in the class, whether people thought of it or not. It's okay. But now there's another one in the chat that's sort of similar that also really is thoughtful and shows that you've been paying attention, which is that someone wrote, for the system schema of the apple, would it be wrong to have drawn a line for the normal force? Now, I'm going to get to the normal force. You'll note it's not a coincidence that I have not said anything about the normal force yet. Like I am about to. Oh, and in fact, yeah, I really am about to. Um, but I'll say this. Like, so it's not a crazy question, but I'll say this. In the, I don't use the words like normal in the context of the system schema. I will use words like that once we get to the free body diagram, like in a minute. In the system schema, what I'm very deliberately trying to do is only use names for objects. Like the system schema, in other words, the word normal force, like some of you have heard it, some of you have seen it online, some of you learned it in high school. It's a thing. Yes, we're about to talk about it. But that too is a very deceptive piece of terminology because the term normal force makes it sound it makes it sound like the force is just normally there, like that it's a force that normally you better put in your diagrams or normally you better recognize, like acts on objects. And that is not true. Like I'll get like we don't what we're trying to get around here too. We're trying to break down the common misconception that forces can just exist on their own. Like despite Star Wars, no forces don't just come along out of nowhere. There's no force that just like is normally there. Even gravity, which would be the closest idea of that, even gravity is only always there because planet Earth is always there. So what we're trying to do here is think of every force only as an actual pull or push between two actual identifiable objects. So if I can, so here in the system schema, I just name the objects and then I connect them together with lines, and the lines are the forces. It's like name the nouns, and then whatever the nouns are verbing each other, that's a force. If that make that probably didn't make sense, but so I will say in my class, I highly recommend that you don't mention anything about normal or anything in a system schema. Just like, and I'll move on, but just like notice, I didn't even mention gravity in this system schema. Like, there's no mention of gravity. There's just a mention of Earth and an apple, and then there's a line between them because that's how we want to understand forces, that they are the interaction between actual objects. So my with all due respect, I'm saying, yeah, like don't even think about normal or anything in the system schema. But but now I want to move to the free body diagram. Yeah, so let me move and yeah, so I'm gonna move to the free body diagram now. Okay. Wait, and thank you. Okay, great. Was that? Wait, I'm just. Oh, that was that person. Okay, thank you, that person, for closing conversational loop. Awesome. And yes, thank you. Okay, so now I'm going to go to the free body diagram. Here's how you do the free body diagram, the pure free body diagram. Rule number one here is that mass that we were depicting before by a dotted circle, we're now going to depict as a point. So we're going to get more precise now and we're going to get more precise and mathematical. So we first take our mass, the apple, and we picture a point at the center of mass of that mass, and we draw a dot representing that point. Now, we're going to take every single one of those lines from our system schema, and we're going to draw it. We're going to turn it into an arrow, and we're going to put each one of those arrows in this diagram. And the way so rule number one is draw a dot representing the mass. Rule number two is for each line in the system schema, make an arrow whose tail starts at the dot and whose tip points in the direction that that force is pointing in. Okay, so first of all, so I'll say that again. So rule number one is you draw a dot representing the mass. Rule number two is you take each line from the system schema and you turn it into an arrow whose tail is at the dot and whose tip is oriented in the direction that the actual force is actually acting in. So like here's my system schema. I start with planet Earth. Planet Earth is pulling on the mass, right? So this picture is just showing you that that's happening. Um, um, but it's not showing you anything about direction. So now I ask myself, okay, well, planet Earth is down below um, the apple, so it's pulling down on the apple. I mean, and gravity is a pull, and Earth is below the apple, so Earth is doing what it's always doing, which is pulling down on the apple. So I draw an arrow pointing down on the apple. Um and I give it some length that approximately in my head is sort of scaled to like how strong that force is compared to other forces in the situation. That's like a rough thing. But and then I go to the other line. The other line is between the table and the apple. So the table is also underneath the apple, right? Just like the earth is. But the table is pushing up on the apple. You want to picture that now, right? Like earth is pulling down, but the table is pushing up on the apple. How do I know that? Well, number one, because it's underneath the apple and it's not a magnet. I mean, it's like resisting. But number two, you know that if the table weren't there, the apple would fall down. But the apple isn't falling down. So presumably the table is pushing up. So I'll draw an arrow for that table that's going up. And I have a rough sense in my mind that I have a feeling, and I think we're going to find this in a minute. I have an intuitive feeling that those two magnitudes are roughly, if not exactly equal. Therefore, I make the sizes of the arrows roughly, if not exactly equal. I mean, that's a rough thing. But if you knew dramatically that one was dramatically stronger than the other, you'd make that arrow dramatically larger. So there's two lines in this picture. Now there's two arrows in this picture. This is a very different picture now, right? Notice, so now we're converting to arrow, and we're doing this in stages on purpose because the first issue for everybody always is what are the forces? Then once we've got them, then the next issue is what direction are they acting in? So now we've got that. Notice one of the reasons these forces were depicted as lines as opposed to arrows is it's trying to express Newton's third law. This picture is trying to get across that each force is a symmetric interaction. It's trying to get across that if the earth is pulling on the mass, it's also true that the mass is pulling on the earth. Like, and that's correct, right? It's a tug of war that's going on. But now that we've gotten that identification, we're focusing in on the object and saying, here's what's happening to the object. It is being pulled down while also by earth, while also it's being pushed up by the table. Okay? Um, looking at the time, looking at the sheet, 1 second. I just want to see. I'm just looking where when friction. Yeah, okay, okay. Um, so rule one was um drawing a dot. Rule two was taking each one of those lines and turning them into an arrow. And for sure, in a pure free body diagram, you should have exactly the same number of arrows as you had lines, in the system schema. Now, rule number three. Now, here we go to the direct chat person's question. Now, in rule number three, we are going to start putting names to these forces. We are going to start labeling these arrows because pretty shortly, like these arrows are going to start turning into symbols that are going to go into the equation, which again is the purpose of all of this. The whole purpose is setting up the left side of the equation. So yes, now in step three, we're going to give names to the forces or symbolic expressions that can be used in equations. So yes, this arrow that's pointing down, this is the weight of the object, right? I mean, this is Earth pulling down on the mass. We said that that phenomenon, gravity, is called the weight of the apple. And what we decided Monday is that symbolically, expressively, quantitatively, if you want to capture the weight of an object, it's always its mass times that 9.8 number, lowercase g. So it is true that I'm now giving that name, I'm calling that downward arrow mg. And it is absolutely true that just like in every system schema, the earth will be depicted right away in every single system schema. By the time you're converting things into a pure free body diagram, every single pure free body diagram ever in classical mechanics in physics 203, every single one will have a down arrow labeled mg in it every time because every object has weight. in classical mechanics. So you can always just draw that arrow first and you're always safe to do that. Okay, so that's one name for what. And sorry, and one last thing. Notice now. Now I'm really focusing in on what's happening to the mass. Like the Earth is no longer in my picture. Now there's just the effect of the Earth is in my picture, and that effect is called weight, mg. Right now I'm like really zooming in on what is happening to the m. One thing is an mg that's pointing down. I use the Earth in my other diagram to make me realize that this force is here, but now I'm all about this force. So similarly, there's a force pointing up from the table. I identified that the table is pushing the apple, so that's what let me know that there's a force happening there. Now, when I'm focused on, now that I believe with confidence that there is an upward pushing force on acting on the apple, yeah, I'm going to give a name to that force because I know I just now that because I don't care anymore what caused it. I just care that it's there. So yes, I'm going to call that force the normal force. Now let's talk about this for a second. Hold on. So this is what someone was asking about in the chat. I say it comes up now in the free body diagram. So mg. Okay, in this diagram, there's two forces, the mg, the weight, and n, the normal. I want to now talk about this business of the normal force, but the first thing I want to say about it is not in every diagram. mg is. mg is in every single diagram without exception. The normal is not in every single diagram. For and so the name normal is deceptive. Um, just cause gravity is there does not mean that normal has to be there. So what does the normal mean? Okay. When objects are touching, exerting contact on one another and exerting forces that way, we have special names for the kind of contact that objects can be in with one another. We have special names for the kind of contact so that once we've identified the contact is happening, then we don't care what the objects are that are doing the contact. We care what kind of contact it is. So first of all, if some kind of line, some one-dimensional type of object is pulling on another object, i.e., for example, if like a fishing line is pulling on a fish, or a tug of war rope is pulling on a child, or a rubber band is pulling on a paper clip. When a line is pulling on an object, that kind of pulling, and remember, pull means toward, push means away. So when a line, when the edge of a line pulls on an object, We call that force tension. We talk about the tension in a rope, or the tension in a rubber band, or the tension in a string. Okay. And I'm not saying that's happening in this problem. I'm just saying it as a concept. So if ever you have a one-dimensional line at the edge of it pulling on an object, you like then once you get to the free body diagram, like in the system schema, you might write rope or line or rubber band or whatever. Then in the free body diagram, the the word for that force would be called tension, and so you would just put a big capital T in the diagram. Okay, that's if a line is pulling on an object. However, so that's like point number one. Sorry. However, point number two, and that would just be one line, it would be one line in the system schema and one arrow in the free body diagram. However, when a surface 2D pushes on another surface, does this sound familiar? Like we were alluding to this a few minutes ago. Then, when a surface pushes on another surface, then there's two forces that come into play. This is why two lines get drawn in the system schema. Sorry. Well, sorry. What I mean to say is when a rough surface. Sorry. When a okay. When two surfaces press against it, when two surfaces are pushing against each other in any way, like my two hands right now, right? Okay, you can think of a plane of like surfaces are planes, two-dimensional regions of space, regions of matter. You can think of a plane between my two hands, right? And one way in which my hands are touching is they're touching against each other. They are exerting forces against each other, i.e., perpendicular to the plane of contact. Like right now, the plane of contact is like this, and they're going like this. So the plane is like vertical, and they're pressing horizontally, right? One way in which surfaces press against each other is literally that. They press against each other. If you really step back and think about it, when they're pressing against each other, that means they are pushing perpendicular to the plane of contact. Now, the word for perpendicular in math and physics is normal. Normal doesn't mean average. It doesn't mean typical. It doesn't mean ever present. Normal means perpendicular. So when we talk about, and I see that in the chat. I'm going to look at that in 1 second. So the first thing I'm saying is if two surfaces come together, the way in which they press perpendicularly to the plane of contact is what we call the normal force. It's really the normal component of overall interaction. It's a direction. Normal is all it is. And it means one surface against the other. I'm totally going to look in the chat. Actually, am I going to? Yeah, I'm going to look in the chat. Oh, yeah, really good. I'm not, yes, good. Person said in the chat, like, I remember hearing about the force of inertia, and I was really wondering what that really meant because in words I can't see it. Yes, honestly, and I won't, I'll try not to wrap. Great observation, reflection. Thank you. I don't want to rabbit hole, but I'll say a lot of why I'm like over talking all of this, as I always do, is because there's so Newton's laws are a lot easier to follow in a way than like the kinematic stuff we were doing before the exam. In a way, they're easier to follow. But in another way, they there's so much room for misconception and misunderstanding and bad language in even in textbooks and on the web. Like, right, there's people say things all the time like force of inertia and stuff, and it sounds really mysterious, and it ends up getting problems really wrong. Like, right, there's no such thing as the force of inertia. I totally agree, but I mean I hear that all the time also. Like, you're not crazy, but that is crazy. Okay, so normal force is like one of those things. Normal force is a real thing. We do care about it. We do need to understand the physics, but it's very easy to misunderstand. Like very easy to misunderstand. So what I'm trying to drive home right now is number one, normal means perpendicular. And it only comes up if two surfaces are pressing against each other in a perpendicular way, like i.e., perpendicular to the plane of contact. But the reason we care so much about this, and if there aren't surfaces, then there isn't a normal force. Like, by the way, that example of the football yesterday, Monday, like if you just have a football in free fall and you do the free body diagram, you'll have an arrow pointing down for mg of that football that's in free fall, and that's it. There won't be any normal force. Like something in free fall, there's no surface pressing against it. There's no normal force at all. There are often situations where, or someone going fishing, like bringing up a fish on a line, there's no normal force there. Anyway, where there is a normal force is if two surfaces are pressing against each other. And one of the reasons we make a big deal of focusing on the normal force is that now here's the kicker of all this. The reason that I originally said in the system schema, if you've got two rough surfaces pressing against each other, oh, then you would draw two lines. Now, again, in the case of the apple, in this situation, apparently there is no relevant roughness, so we didn't draw two lines, right? But if it had said the table is like rough and has a coefficient of 0.3 or something, then we would have drawn two lines to capture the situation. And the reason is in the real world, as managed by physics, if two surfaces are pressing against each other and they are rough, then if you think about it microscopically, like the edges of the surface, like have lots of little ridges and crests and troughs, what do they call them in English muffins? Like nooks and crannies, right? Like my hands seem kind of smooth, But if I like zoomed in on them microscopically, they're rough, they're like very bumpy, right? So when my hands press against each other, the bumps kind of lock into one another like teeth of a comb, teeth of two combs, like pressing against each other, right? The bumps, the nooks and the crannies of my skin kind of like get locked in with one another. And so the harder I press down my hands together, the harder it is for my hands to rub over one another. In other words, the more there is a perpendicular force, if the objects are rough at all, the more there will be a parallel force. The more there will be a push parallel to the plane of contact, like along the plane of contact, like sliding will occur, sliding resistance will occur in addition to the pressure, right? And the rougher the surfaces are, the more this will produce that. Or conversely, given a certain roughness, the more you press together, the more you get pressing or pushing along the surfaces. Well, you see where this, you see what this, so whenever you get a perpendicular, if surfaces are rough, a perpendicular force will bring with it a parallel force, and that parallel force, so parallel, like parallel to the plane of contact, and you know the word for that is called friction. Now this is a mouthful, and this is all, by the way, not a sidebar. I mean, this is not a tangent. Like this is the point. First of all, somebody asked about the word normal before. Second of all, I'm really trying to show you now. I'm trying to show you like why you draw two lines in the system schema anytime you have rough surfaces pressing against each other. Because when you have rough surfaces pressing against each other, then you have this force, but you also have that force. So you're going to have two arrows in the free body diagram if and when the surfaces are rough. Now, again, in this apple case, they're not. So, I mean, in that sense, this is like a general sidebar. But the final thing I'm trying to say now, and I'll go back to the apple now with 7 minutes, is that vocabulary wise, then, I'm saying there's from here on in, what the Earth causes is weight, gravity, which we're going to designate as mg in all of our diagrams and equations. But then everything else is a contact force of some kind. It's either like a pulling along a string or it's pushing somehow along a surface. We have names for all those contact forces. This from now on is called normal. Well, sorry, let me start again. This is called tension. This is called normal. And this is called friction. And so, yes, back to the apple. The free body diagram of the apple then is mg down, normal up. That normal force, that n, is just a name for the fact that there is a table underneath the apple pushing up on the apple. And so we call that the normal force. From the table is exerting a normal force on the apple. Similarly, by Newton's third law, the apple is exerting a normal force on the table, but that's in a different diagram. But I'm just saying. So now we can use the word normal and put it in our calculations and all that, and we no longer have to care whether it came from a table or it came from a floor or whatever. But that's what normal means. So normal is the perpendicular push from a surface onto another surface. It's only there if there are surfaces pushing against each other. Last thing, is it always there if there are surfaces? Yes. If there are surfaces pushing against, if a surface is pushing on another surface, then it's exerting a normal force. If the surfaces are rough, then there will also be a friction force. In other words, you might want to write this down. So I'm saying, can you have gravity without a normal force? Yes. Can you have a free body diagram or a situation without a normal force? Yes. Can you have surfaces pushing each other without a normal force? No. Can you have Surfaces pushing against each other without a friction force? Yes. So you can have a diagram that doesn't have a normal force in it. Or you can have a diagram that does have a normal force in it, as ours does, but doesn't have any friction. But there's no way you could have friction unless you have a normal force. Okay? That for what it's worth. So this is our free body diagram. This is our pure. Oh, thank you. Awesome. I love it. Alexa, since that's not private. Okay, and there's things in the private chat. Let me pause for a second. And this may be where we're. Oh yeah, right, right. So if a surface is smooth, so this says in the chat, would there be friction in like a smooth surface, or would that friction be so minute that it can be ignored? Right, right. If a surface is smooth, then that means the friction is small enough to be ignored, which basically means that even that any measurement equipment that we had to measure everything else in the problem wouldn't pick up on the friction, right? And the way you know that on a practical level, like in problem solving, if the problem doesn't mention any kind of roughness, if the problem does not make an explicit point about giving you a measurement for roughness, then you can assume, you can infer that it's smooth enough for the roughness not to be making a measurable difference. Right. If that, yeah. So yeah. Um, we have 3 minutes. Let me just go back to the sheet and see. So this would be the pure free body diagram. This is now I will tell you since we only the next step. Okay, we have 1 minute left. If you're doing a Newton's problem in general, then you do step one, step two, step three would be Newton's second law and possibly Newton's third law. Step 4A would be draw the system schema like we just did. Step 4B would be from that, draw the pure free body diagram like we just did, convert your lines into arrows. Then step 4C in general, we're not going to do this right now, would be that from your pure free body diagram, you draw a component free body diagram, which would mean you would take any, just briefly, you would take any arrow that was off axis and you would divide it, you would break it up into components that lie along X and Y axes, like we did with velocities and displacements in your exam, right? Any diagonal lines or whatever, you'd break up into a vertical line and a horizontal line. And then you would, from that, create a diagram that only had a bunch of arrows that were parallel and perpendicular to each other. And from that, and this is the last thing I'm saying because I know it's class, and then step 4D always would be to take Newton's second law and write it as separate equations on separate axes. And from your component diagram, every single arrow that's going vertically, either up or down, you would plug it to the left side of F net equals MA, and all the horizontal arrows you would put into a horizontal version of F net equals MA. And then you divide everything by M and you get A. Like that's the procedure. So we obviously we're going to stop now because it's 10:41. So keep on roll. Just if this helped you with the homework at all and you want to revise this weekend before I even give it back, please do. If you're still waiting for, then don't. Then give yourself a break, and I'll see you on Monday. Okay, thanks. Have a good day.
Thank you,
Yes, good.
Professor.
Thank you. Have a good day. Thank you.
Bye.
Have a great day,
Bye.
Professor.
I think yes, you too. I love that. Okay. Okay. I'm stopping the recording. Going once.